Hi, welcome to the Assembly Language Primer for Hackers Part 1. This is going to be the first of many more videos to come on the basics of assembly language. Now, the reason why I made this video is basically I received a lot of requests for in-depth video tutorials on exploitation techniques such as buffer overflow exploitation, format string, etc., as well as for reverse engineering. Now, what I understood is that if I dive into those topics without people having an understanding of assembly language, then it would be probably impossible for them to gauge or understand exactly how to go about those processes. So that's why I realized that probably an assembly language primer is the best place to begin. Now, this primer is by no means an exhaustive guide to assembly language. You will need to go ahead and supplement this with a lot of other reading. However, if you've never started assembly language before, this can help you get started very fast. So let's now move on to the actual presentation. System organization basics. So in any given computing system, we have the CPU or the central processing unit. Then we have memory, which is where things are stored at runtime, which would be your RAM. And then we have input-output devices, which would be your keyboard, your monitor, your mouse, etc. Now, the way in which these three basic building blocks communicate is using the system bus. Now, we need not get into too much of detail into exactly what the system bus is composed of, the control bus, the data bus, so on and so forth. We'll try to keep it at a very high level, and that too with enough depth so that you can start programming, as you will see in the later videos. So now let's dive into the CPU. So basically the CPU consists of four parts, very broadly. The first is the control unit. This is the place in the CPU which is responsible for actually retrieving and decoding instructions, as well as storing and retrieving data from memory while the CPU is actually executing instructions. The second block is actually the execution unit, which, as you can easily understand from the name, is the place where the actual execution happens. Now, when a CPU is actually executing instructions, it actually requires some internal memory locations in order to do those calculations. These are called registers. So think of registers as some sort of internal variables inside the CPU. And the value of these registers keep changing depending on what the CPU is actually doing right now. Finally, we have the flags, which are actually used to indicate various events when the execution actually happens. So as an example, let's say we have something called the zero flag, which is nothing but whenever any instruction results in a zero, let's say you go ahead and add two numbers or subtract two numbers and the result is zero, then this flag is appropriately set. So we'll get into the details a little later of what these individual elements actually do and mean. So what is most important to understand from a CPU perspective is the CPU registers. And this is what we'll be using for most of our assembly language, I would say, programming. Now, very broadly, there are four kinds of CPU registers. The first is the general purpose CPU register. Now, there are approximately 8 general purpose CPU registers: EAX, EBX, ECX, EDX, ESI, EDI, ESP, and EBP. These are generally used during various calculations which happen inside the CPU. We'll dive into more detail about these registers in the next slide. The second kind of registers is the segment registers, which is CS code segment, DS data segment, SS stack segment, and then others ES, FS, and GS, which are generally pointers used for other segments. Then we have the instruction pointer register, EIP. Now this is probably the most important register from, I would say, an exploitation perspective or a reverse engineering perspective. Simply because this register, EIP, points to the instruction which the CPU is executing at this point. Then we have the control registers, CR0 to CR4, which are internal to the CPU for various calculations. Now, you don't need to by heart all the register names. Generally, as you start programming more and more, they'll come naturally to you. What you need to remember most is that we'll be using the general purpose registers for most of the assembly language programming. And from an exploitation perspective, we will always try to control the instruction pointer register. Now let's look into more details about the general purpose registers. EAX is nothing but the accumulator register, as it is called, and is generally used for storing operands and results data. EBX, or the base register, is generally used for storing pointers to data. ECX is also known as the counter register, is generally used in loop operations and string operations. EDX is the data register. Generally, it's also used as an input-output pointer. ESI is more of the source index. DI is the destination index. ESI and EDI are basically data pointer registers used for various memory operations, more generally used for string operations. ESP is the stack pointer register. Now, ESP always points to the top of the stack. If you don't know what the stack is, we'll deal with that in the next couple of slides. EBP is nothing but the stack data pointer register. Now, don't get worried if at this point you do not understand exactly what all this means or how this is going to be used in assembly language. I just mentioned what the registers are for the sake of completeness. When we actually get into the programming, you will understand how these are used in order to write code. So don't worry. There is one important thing which you need to know about a couple of the general purpose registers, namely EAX, EBX, ECX, and EDX. Now, one thing which I forgot to mention is the general purpose registers, or any register in IA32 architecture, is 32 bits. So now let's go ahead and look at what is that property which EAX, EBX, and ECX and EDX share. Now, it is possible to access the first 16 bits of EAX by referencing it as AX. And it is now further possible to access the first 7 bits and the next 7 bits of EAX by referencing it as AL and AH. A is A high, AL is A low. Similarly, EBX, you can access the first 16 bits by just referencing it as BX. This would be BH and this would be BL. Now, once again, if this is confusing, you'll find out how this is all used during instructions. But you just need to remember is that among the general purpose registers, these 4 registers allow selective access to their lower order bits by using a different name, which is AX, AH, AL, or BX, BH, BL, CX, CH, CL, and then DX, DH, DL. Let's move on to the next slide. Okay, so we've covered the CPU in enough detail so that we can begin programming. Now let's look at memory. So the first thing one needs to understand is the virtual memory model. Now, what is the virtual memory model? Now, whenever any program is executed, it is overlaid as a process in memory. Now, the way it is laid out is that every process gets laid out in the same virtual memory space, regardless of the actual physical location of that process. So imagine that you have 2 gigs of RAM, then a new process could be overlaid anywhere in the actual RAM. However, what the processor and CPU do together, the processor and the operating system do together, is that they abstract out all of these complicated memory layouts from the process itself. For the process, it almost feels as if the entire system is for itself, it's the only process, and it is running in the entire space. And no other processes exist. So we won't get into too much about the virtual memory model right now because it can be a bit confusing. But what you need to understand is that every process is laid out in the same virtual memory space, right? So how exactly does a process look like when it is laid out in virtual memory? That's where we get into the exact program memory layout. Now, generally a process is laid out in this order. So what we have is various segments in the program memory. We'll get into in-depth discussion about them a bit later. I just want to mention what they are right now. So the first segment which is laid out is the dot text. So this is the actual program code. If you notice, this is laid out in the lowest memory value possible, which is 080480 So this is laid out from low memory to high memory. Now this contains the actual program code, which is the dot text segment, which is where the executable instructions are there. Then we have the dot data segment. This is where any data which has been initialized to a value is stored. Then we have the dot BSS segment, which is where all uninitialized data is stored. Then we have the heap, which is dynamic memory. Now we are all familiar with malloc, right, which we've been using in C to generate dynamic memory. Whenever you call malloc, it returns a pointer to some memory in the virtual memory space, and this is where it is, the heap. Then you have a lot of unused memory, and then finally the stack. Now most generally the stack is used for storing arguments which are passed on to functions as well as local variables in functions. So as one can notice, the stack is actually laid out in the highest memory location possible. And thus the stack generally grows down the memory, which is from high memory to low memory. So, I mean, you just need to understand many of these things for now. Even if you don't just take them for granted, when we start programming, many of these things will be very, very clear. So do not worry if you're lost right now. So now let's look at the stack in more detail. This is a very important piece of the program memory. So a stack is a LIFO. What does that mean? It is basically a last in, first out data structure. So basically the stack, as we discussed in the last slide, is laid out from high memory to low memory, right? Which means the stack grows down the memory. And ESP, as we had seen previously, points to the top of the stack. Now a stack supports only two operations. The first operation is a push operation, which is actually pushing data into the stack. Now, as soon as we push a value, let's say A0, 20, 30, 40, all in hex, what one needs to do is update the stack pointer. So now ESP will point to the top of the stack, which is after the addition of the new value. And once again, when you're done with using that value and you want to remove it from the stack, you use the pop operation. Once the pop operation is used, the data is removed from the stack, and once again you need to go ahead and fix ESP to point to the top of the stack. So now you understand why a stack is called last in, first out. Anything which is put inside the stack is the first thing which will have to be removed from the stack in order to go further deep into the stack, right? Well, I think we've covered a lot of ground. So this is all you need to know about memory in order to get started. As and where we need more theory, we will dive deeper into it. Now let's actually go on to a live demo of examining memory, stack registers, etc. using a very simple C program and GDB. So this will be covered in the next video. So I hope you like this video. If you have any comments, please go ahead and leave a feedback in the comment section just below the video. This will help me make better videos for you viewers of SecurityTube. Well, that's all for this video. Thank you.